Hello everyone, this is PCB, your trusted PCB partner. Today our topic is, in 4-layer board communication module design, why do digital and RF signals need to be isolated? In modern smart devices, we often see a trend. On a tiny PCB, there are both powerful digital processors and RF modules responsible for communication, such as Wi-Fi, Bluetooth, and even cellular networks. This kind of integrated communication module design certainly sounds very cool, but behind it lies a whole host of enormous and complex design challenges. So today, let's take a deeper dive and talk about what we actually face when integrating these vastly different types of signals, like digital and radio frequency, on a standard 4-layer board, and explore the fundamental reasons why these digital and RF signals need to be so strictly isolated from each other. As an example, here is an RF board that can output 4G to. This RF board covers a frequency range up to 4G. You can clearly see the isolation. There's a section in the middle with nothing on it. On the left is the MCO control circuit, and on the right is the RF circuit. So how do digital and RF signals differ in their characteristics? To understand why isolation is necessary, we first need to recognize the differences in temperament between digital signals and RF signals. Let's take a look at a diagram. The analog signal shown above represents the video signal, while the one below is the digital signal. There are very obvious differences between them. Let's talk about the digital signal first. Its characteristics, as you can see from the diagram, are that the voltage rapidly switches between 0 and 1 with very fast transitions. The rising and falling edges are almost vertical. In terms of noise characteristics, this kind of rapid voltage change generates a wealth of high-frequency harmonics. These harmonics are broad-spectrum noise sources with strong electromagnetic radiation capabilities. As for noise tolerance, digital signals usually have a certain tolerance for the absolute value of voltage, but they are very sensitive to timing. For example, if there is some noise on the high level, it generally doesn't affect the signal. As long as it is recognized as a high level, the speed can be much higher. The same goes for the low level. Even though it's considered zero, as long as it's below, say, 0.5 volts, it will be recognized as zero. So digital signals have a high tolerance for voltage variations, but the actual requirements are low. However, the timing intervals are very important. Next, let's talk about the characteristics of RF signals. Their frequencies are very high, usually ranging from hertz to gigahertz and even up to tens of gigahertz. The signal amplitude is typically small, and the waveform is a continuous analog wave. As you can see here, it's a continuous waveform, unlike digital signals, which are abrupt and discrete. Regarding the noise characteristics of RF signals, RF circuits are extremely sensitive to noise and interference. Even very small amounts of noise can be amplified by the receiver and overwhelm weak, useful signals, leading to a decline in communication quality or even complete loss of signal. Generally, the amplitude of RF signals during reception is quite small, so the amplification factor of RF amplifiers is very high. Therefore, if there is any noise present, its impact will be greatly magnified. RF circuits are highly susceptible to all forms of noise, including power supply noise, digital signal radiation, and even ground coupling on the PCB. This places very high demands on the design of RF circuits and PCBs. Let's take a look at a real-world example. For example, the one on the left here is a digital signal. We can see that there is some noise present at both the high and low voltage levels, but this doesn't really affect it. However, if similar noise were added to an analog signal, it could have a significant impact on the signal integrity. Why do digital and RF signals need to be strictly isolated, and what potential hazards are there? You can see from this board that both sides have been clearly separated. Digital and logic circuits are kept apart. It's precisely because of their different characteristics that if digital and RF signals are not effectively isolated, they can cause serious mutual interference. Digital signals can contaminate RF signals, starting with radiated interference. The broadband electromagnetic radiation generated by digital signals, also known as EMI, can directly couple into sensitive RF circuits, especially the front-end RF paths or RF front-end pins. It's like someone shouting loudly in a quiet library, directly disturbing others. Conducted interference. Digital signals can also cause interference through shared power supplies. They can be conducted through the network into the RF circuit, creating power supply ripple or ground noise, which directly affects the stability of the RF chip. That's why we need to isolate both the power supply and ground. What are the potential hazards? First, there is a decline in communication performance. The RF receiver's sensitivity decreases, transmission range shortens, bit error rate increases, and in some cases, normal communication becomes impossible. Second, there is a risk of product functionality being severely affected. Serious interference may cause the RF module to fail or malfunction indirectly. Third, there is the risk of failing EMC certification. Digital interference may cause the product's external radiation to exceed standards, making it impossible to pass EMC certification. Fourth, such cross-interference is difficult to debug. It is often extremely complex, hard to pinpoint and resolve, and consumes a lot of time and resources. The cause of the interference is not always clear, and it is difficult to accurately determine which chip or which line is responsible. All you can see is that the signal on the line appears normal, so debugging becomes very challenging, and the difficulty is quite high. How to lay a good foundation for this integrated design. Integrating communication modules on a 4-layer board must have a natural advantage over a 2-layer board because it has better knowledge and can provide a dedicated ground plane. The complete ground plane in the 4-layer board is the basis for realizing digital and reasonable design. It can provide a stable return path for each signal and serve as a natural switching organization. Then there is the power plane. The independent power plane also helps to provide a stable and low noise common link for digital and RF. It can provide more firmware layers and allow digital signals and RF signals to be limited to different signal screens to further reduce. This is already very obvious in this version. Today we learned about digital signals and setting signals, their differences, and the potential hazards of not isolating them. We also initially realized the advantages of the 4-layer version in providing an isolation foundation for this integrated design. In the next class, we will use a specific case to demonstrate how to apply these isolation principles and unlimited measurement on the idea board to successfully integrate digital processing design statistics modules. If you like this video, please subscribe to my channel to get more videos. Thank you.